There we go.
Okay, let's take a look at this limit stuff we were talking about last time. Remember, just to kind of put things back in perspective after the weekend, we had talked last week about limits. We spent quite a bit of time talking about sort of what conceptually limits like, and we talked about ants and whatnot. And initially we looked at some methods of evaluating limits by looking at graphs, right, and just seeing where the ant would anticipate stepping, or even numerically by making tables. But we closed out the week being a little more mathematical about this, being a little more exacting. We started looking at analytical techniques. How can we algebraically come up with the exact answer without having to make an estimation? You know, it sounds a little hokey, based on a graph or a table. And what did we decide? When we're trying to evaluate limits analytically, we started to develop kind of a strategy. What's the first thing we always try to do? Plug it in. Yeah, first thing is we always want to just try direct substitution or direct evaluation. And it might work, right? When we try direct substitution, there are always going to be three possible outcomes. And we'll just talk about how to deal with each of those outcomes. Now, one of them is, the most obvious and probably one we're hoping for is what? When we try direct substitution with a limit. It works, yeah. We get an answer that's just a rational number, right? For example, what if we had something like, let's just take a quick example to illustrate this. The limit of x squared over x plus 3 as x approaches 1 is what? Yeah, 1/4, right? If I just evaluate this directly at x equals 1, I get the answer 1/4, and I'm done. That's the end of the, right? We took the limit, we evaluated the limit. That is the y value that the ant what? Anticipates stepping on. When he steps on an x coordinate of 1, he anticipates stepping on a y value of 1/4, and we're done. So one possible outcome is that. We get an answer of a over b where b is not 0. Could a be 0? Yeah. Sure. 0 is just a number, isn't it? Right? 0 divided by another real number is always just 0, and that's fine. That's just an answer that we're fine with, and that's it. So that's scenario 1, the easy one. We get an answer. Okay, what else could happen? Well, we could get 0 on the bottom. We could get a number divided by 0. Now, what did that mean? Say it again. No, that one's not the more work one. This one we're actually done with. It's undefined. Yeah, it's undefined. We are going to go a little bit further with this outcome soon. We can be a little bit more specific, but not much. We're essentially done. No matter what we know here, the limit does not exist. We could maybe be a little bit more descriptive about what's it doing and not existing at the same time. It might tell us something about the shape of the curve that we're looking at, but we'll get into that. For now, it's perfectly adequate for us, until we go a little further, for us just to say no limit. That's the answer. There is no limit. There is no one place the ant anticipates stepping. Now, what we're going to come to associate this with is a vertical asymptote. When we get a 0 on the bottom, but not on the top, that's going to be a vertical asymptote, and we'll discuss that in more detail later. I guess I don't need to, everything's not that important, is it? Maybe, I don't know. It's like I'm shouting at you. So that's the other possibility, and we're done. If we get a number divided by 0, no limit, done. Move on to the next one. Okay, the third possibility was the one that we started spending a little time with, and this is the one that requires a little algebra. What happens when we get something like that? What do we say to that, man? More work. More work. Okay. The third possibility, if we get 0 over 0, that is That's an indeterminate form. And as the name suggests, could be lots of things, right? We don't know yet. And that's the one that we always equate with more work. Okay? And the more work part is what we're going to talk about. What are some techniques we could use to maybe deal with that third situation? We looked at an example, I think last time. Let's just remind ourselves kind of what we were doing. What if we had something like this? The limit of x squared minus x minus 12 over do that right? -3. Yeah, that should work, shouldn't it? Yeah, what do I get if I try that? Always get try-direct evaluation. 0, 0, right? Does that make sense? On the top, I'm going to get -3 squared is 9, minus -3 is plus 3 is 12, minus 12 is 0, right? Bottom, I get 9 minus 21 plus 12, also 0, right? So 0 over 0, indeterminate, more work. Now, what did we say about this on Friday?
Factor.
Okay, yeah, this is an example where when I've got a rational function, and let's make sure we all understand what that means. A rational function, in fact, I'm going to just take one other page here. Let's define this. This is something we'll talk about a lot. A rational function is really just, here's the easiest way probably to define it. Ratio of polynomials. So we'll get something like this. R of x is a rational function. It can be written as f of x over g of x, where both of these guys are polynomials. And what's a polynomial? Might as well remind ourselves of that. What's a polynomial again?
Squared.
Poly means what?
Many.
Many. And then nomial, I'm not sure where that comes from, but it just means many terms. Okay, yeah. Not even sure how the nomial part gets in there. But all a polynomial is this. Like, here's some examples of polynomials, right? We could say something like 2x cubed minus x plus 3, 4x to the 4th plus 2x cubed minus x squared plus 3x minus 11. What do those have in common? What are the rules for a polynomial? Just a sum of a bunch of terms. What does each term have to, what are the criteria it has to meet? What about the coefficients? 4, 2, -1, 3. And that's actually a coefficient too. What's the power of x there? 0, yeah.
One coefficient.
One, okay, each term has a single coefficient, but that would almost, pretty much always be the case. What would be, I mean, it's a good thing to point out. What about do you notice, I mean, I could let me make this a little funkier here. How about if we had something like, this would be okay. I didn't write any like this, but I probably should have. What if we had something like square root of 2x minus pi? That's fine. So what sets of numbers are included? You want to pick the broadest set of numbers that's inclusive. It's not just integers, is it?
Real numbers?
Real numbers, yeah. That's it. The only only thing we can't have for the coefficients is an imaginary number. Any real number is okay. Okay? What about the exponents? Now, I wasn't being overly general with those. That's very representative of a polynomial. What do you think? Now, that's an x to the 1, and this is an x to the 0, right? So what's true of those exponents? Yeah, sure. Are any of them negative? Nope. Are any of them irrational? No. In fact, they're all really just non-negative integers, aren't they? Now, what's that? And that's fine to call it that. Does anybody remember what that set is called of non-negative integers? This is this isn't a big deal. We said that like the natural numbers, we never really use that set. The natural numbers are just the counting numbers, 1, 2, 3, 4, 5. And then what do we call the set of natural numbers plus 0? Remember? Say it again. Non-negative integers is fine. That's perfectly descriptive. We actually do that's for whatever reason we give that set its own name. We call it the whole numbers. Does that ring a bell? So this would be technically then, if we're defining a polynomial, we'd say it's the sum of terms such that the coefficients are always real numbers, and the exponents, the powers of these are powers of x. The exponents are contained in the set of whole numbers, and that's it. Okay, so those are polynomials. A rational function is just a polynomial divided by a polynomial. That's it. Okay, and we'll do a lot of work with polynomials and rational functions. So we said then on Friday, we said that when we're trying to take a limit of a rational function and it's indeterminate, if we get that 0 over 0 form, then the solution or the strategy for us is always to try to just factor it and then cancel the factors, right? And what we did was really tricky. It doesn't seem like much. What we ended up doing was actually taking this function that's got a hole at -3 and trading it for a new function where we just fill in that hole, which we're going to use for the purpose of evaluating our limit, right? So in this case, what does that factor into? What's the numerator? What's that polynomial factor into? Say it again?
X minus 4, x plus 3.
Okay, good. X minus 4, x plus 3, bottom one.
X 4 plus 3.
Say it again?
X plus 4.
Good. X plus 4, x plus 3. That makes sense? Okay. And then algebraically, we can cancel the x plus 3's, and those are the offending factors. Those are the guilty parties, right? Those are the ones that were causing this to be 0 over 0. Once we cancel those algebraically, now we can evaluate our limit directly and just get an answer, right? And so what do we get? If we let x approach -3, we get, what, -7 over 1? So -7 is our limit? Okay. Make sense? Okay, and I didn't give you guys an assignment on this because I was so sure that we were going to get our Math Excel stuff today, but we didn't. So I'm sure it'll show up today, and we'll go down to the lab and sign up tomorrow. And we might as well just do this assignment on Math Excel. I'm sure we'll get these things. I'm sure we will. They assured us they were going to overnight them, and they should have been here on Friday, but I'm sure maybe they just got here late on Friday or something. I haven't seen them yet. Anyway, that's our first strategy. Now, we had just pushed into talking about the next look, and I think we didn't get very far with it, but we said something like this. Let's see, here's what we have. Okay, first thing we'd obviously try is evaluating directly, and we'd get 0 over 0. And do you remember what our strategy was in this case when we had this isn't a rational function, is it? These aren't polynomials, but we've got an indeterminate form with a radical in the numerator in this case. Could have been the denominator. What did we do? Remember what our strategy was.
We multiplied by x.
Ah, good. Okay, good. We're going to multiply the top and the bottom. We're going to multiply the function by 1 in the form the conjugate of the top divided by itself. Okay, and the purpose of that, and I don't want you to, thank you, I don't want you to just memorize. If you just memorize stuff, you're going to forget it. The facts are disparate and they are not organized well in your brain, and you'll just forget them. But think about this in terms of a strategy and an overall concept, and you'll remember it forever. The reason we're doing this, remember, is because when we deal with conjugates, and these two factors, remember, are conjugates. That's all it means, right? It means two binomials, the sum and the difference of two terms multiplied together. Those are conjugates. When I multiply the conjugates together and I FOIL them out, remember what happens. First times first is a squared. The outside would give me minus ab. The inside would give me plus ab. And the last would give me minus b squared. But notice what happens. The cross terms always cancel. So FOIL just becomes full for conjugates, right? And that's an advantage to it because look, we end up with the square of the first term minus the square of the second term, and that's a great solution for our particular problem because the first term is a square root. When we square it, the square root's going away, right? So that fit our particular needs perfectly. Okay, and so when we did this, when we expanded this out then, what did we get on top? Well, let's see, there's our A and there's our B, right? So we just got the square root of x minus 1 squared, or excuse me, x plus 1 squared. So that's x plus 1, right? That's my A squared minus 2 squared. That's my b squared, right? Okay. On the bottom, it sort of looks like a mess. And initially, you might ask, when you're looking at this, say, well, what's the point? It didn't make it look any simpler. The bottom still has that square root stuff in it. I mean, that doesn't look a lot better than that did. However, it is. Because if we evaluate this factor directly, it doesn't go to 0. Right? Does that make sense? It's something you want to kind of keep in the back of your mind here. And I'm just kind of thinking out loud, just telling you, it's kind of a way to think about this as you're doing these. When you're taking limits, don't be afraid to introduce ugly-looking expressions. Because remember, when you evaluate the limit directly anyway, all the values of the variable are going to become numbers. We're going to just crunch this up into a number anyway, right? So in a sense, limits are always sort of self-cleaning entities. They're always going to, as soon as you plug them in and evaluate directly, it's all going to be fine. They're just going to turn into a number, right? And so that, even though that looks ugly, no big deal. Just give me a number. But look what does happen here when we simplify this. On the top, we get x plus 1 minus 4 is what? X minus 3. On the bottom, we've got an x minus 3 times the square root of x plus 1 plus 2. Well, what do you notice? Yeah, once again, we can cancel the guilty parties. The offending factors are going to get canceled. And on the top, we're just left with a 1, right? And now, once those factors have been canceled, we can just evaluate directly and get an answer. So if we take the limit, if x goes to 3, what do we end up with? On the top, we got a 1. On the bottom, we get Yeah, square root of 4 is 2, plus 2 is 4. Done. How about that? Right? So this is what we technically call in calculus, if we had to put a title on this, this is a rationalizing strategy. What do they call it in the book? Rationalizing technique, probably. Not that it really matters. Yeah, rationalizing technique. But that's the important one. It's a rationalizing technique or strategy. How come? Because this looked irrational. I had a square root function there. And think about, unless it's a square root of a perfect square, square root of 2, square root of 3, square root of 5, square root of 6, those are always going to be irrational numbers. Right? And so we got rid of that irrational problem with that square root by multiplying by the conjugate and getting it to go away out of the numerator. Okay? Make sense? So now we got two strategies. Okay, this next one is sort of a freebie. You're going to know what to do on this one without even thinking about it. Okay, what about this guy? What if we have something like this? Okay, if I evaluate that directly, what do I get? Yeah, 0 over 0, again, right? Or I wouldn't have picked it probably. So this also falls under that broad category of more work. Now, this one involves a bunch of fractions, right? What do you suppose we do here? Exactly, yeah. We are just going to, all we do here, this is no big deal. All we're going to do is the normal stuff we would do if we were trying to simplify a function that involved fractions in the top and maybe fractions in the bottom. And let's just remind ourselves what we always do with that. If I've got, and we're going to do a lot of that stuff this year. If I've got some big ugly function that's got fractions in the top and fractions in the bottom, what we always want to do is take the whole numerator, crunch it down to a single fraction, simplify it to a single fraction. The whole denominator, simplify it to a single fraction. And then if I divide fractions, don't I just flip and multiply by the bottom? Right? So that's my strategy. Just normal stuff. We're just going to rewrite this in a simpler form. Okay? So what does that involve? Well, on the top, if I want to get a common denominator on the top, what's it going to be? Okay, so it's going to be the product of the denominators, right? Makes sense? So I'm just going to, I see what you're getting at here. So on the top, we've got 1 over x plus 4 times 4 over 4 minus 1/4 times x plus 4 over x plus 4, right? And if I'm looking just at the denominator, and we'll get to the numerator, sorry. Denominator is pretty simple. Then in the the numerator, then I've got a common denominator on top of 4 times x plus 4, right? So that's going to be my common denominator, and then I just end up with 4 minus the quantity x plus 4. Agreed? So there's the numerator of that whole thing, almost simplified. Denominator, very simple. That's just x over 1, right? Okay, well, we're getting there. Still indeterminate. I haven't canceled anything yet, have I? So on the top, if I distribute that negative sign, what do I get? 4 minus x minus 4, and so I could go ahead, what I'm really doing is just canceling the 4's, right? So I end up with the limit as x approaches 0 of negative x over 4 times the quantity x plus 4. Minor issue. A lot of you guys, you distributed that 4 because you're great math students and you're always looking for more work to do. Do we want to do that?
Probably not.
It's not a huge faux pas, but there's no need, right? Because remember, when we evaluate this thing, we're going to be plugging in a number for x anyway, aren't we? Right? And so why go through the hassle of expanding something when this x plus 4 is just going to turn into a single number anyway, right? So there's no need to do that. And then on the bottom, we've got our x over 1. So last step, flip and multiply by the bottom, right? So I get negative x over 4 times x plus 4 times 1 over x. When I multiply, I just multiply straight across, so I might as well just do that, right? Now what? Now we cancel. Yeah. Cancel the x's, and I could now just take my limit. Now if I plug in 0 for x, if I evaluate directly, I'm just getting negative 1 on the top, and 4 times 0 plus 4 is
16.
16 total, right? So that's my answer, negative 1/16. So that's probably the easiest, maybe not the easiest to execute. You got to do some algebra there, but it's the easiest in terms of a strategy. It's just what you naturally would do, right? Okay. All right, last thing I want to look at, and this is kind of cool. This is an example of a pretty cool proof that we can do that's very visual. This is a good one. So first I got to introduce you to a new thing in math called the squeeze theorem or the sandwich theorem. Okay, no big deal. What this says is, and this might be slightly different, I think the picture's a little different than the one in the book, but same idea. If we've got these three functions, h of x and g of x and f of x, and so h of x is orange, g of x, the graph of g of x is blue, and the graph of f of x is green, let's say. At least in the neighborhood of x equals a, okay, around that x value. Well, if this is the way the graphs look in the neighborhood of x equals a, in other words, if for all x in some open interval containing c, except maybe at c itself, it's possible that there's a hole in all of these functions at c itself, because we're talking about a limit, right? So don't actually care what happens at x equals, did I call it a c up there and an a down there? I guess we need to make this a c. As long as every place else around x equals c, these functions have this relationship, okay? Right, so in other words, h of x is less than or g of x is greater than or equal to h of x and less than or equal to f of x in the neighborhood of x equals c, right? Then, if the limit of the top function, h of x, as x approaches c is L, and the limit of the bottom green function, as x approaches c, is also L. What does that necessarily say about the blue function that's squeezed in between them? What's its limit have to be? Has to be L, doesn't it? Right? If the blue function is encapsulated between the cap function, the orange function, and the floor function, the green function, and they both squeeze down to a single limit, well then obviously it gets squeezed to that same limit, right? No big deal. That's what I call a picture theorem in calculus. The picture says it all. Okay, so then we know that this limit exists for the blue one and it equals L. Okay, why do I bring that up? Well, here's where that one becomes important. Let's look at the limit of sine x over x as x approaches 0. Okay, if I try to evaluate that directly, what do I get?
0, 0.
0 over 0, so it's indeterminate. Now we could just graph that function on our calculators and see what it is, look at the trend, but let's not. Let's come up with a real analytical proof of what that limit actually is. And by the way, the limit is 1. For whatever reason, and we'll see a proof of that, this is one of our special, this is really the only special trig limit you have to know. Anything else can be derived using trig identities from this one limit. And that's it. Okay, let's prove that though. Here's a way to do it. Let's see, I gotta draw a little picture. So we're gonna go to the unit circle for a moment. So why don't I get you? Oh, this is cool. I get to play with my toys just for a second here. I can make this look pretty good. Let's see. Oh, there we go. Okay, so there's my unit circle. Okay. Now let's on the unit circle. So the radius, what's that mean if it's unit circle? The radius is the radius is 1. Radius is 1. In math, when we talk about a unit, anything like a unit vector, maybe not so much this year, but next year for you guys, or anything that's described as being a unit entity. Unit means 1. Unit always means 1. Unitary means like it's 1. So radius is 1, centered on the origin. Let's look at an angle. We'll call this theta, or x, I guess I should say. I used x. Okay, let's look at a couple areas that we could define based on this unit circle. One of them is, let's make a green triangle. It's a right triangle. Okay, what's the area of that green triangle? If the radius is 1 and the angle is x. Think in terms of trig. What's the area of a triangle in general? Half the base times the height. What's the base? 1. Okay, so we just need to know, if we knew what this height was in terms of the angle x, what have you said? Okay. Actually, the base isn't 1, is it?
No.
Never mind. Okay, so what we want to do, you know what? I drew that wrong. Hang on a second. I drew that wrong. I want to draw a different one. That way it's harder to do. Let's do it this way. I want to draw it like this. Is that what I want? Is that what I want? No. Oh, never mind. I want this. There, that's what I want. Okay. That's what I want right there. Okay, now what's the base? Much better. Much better. Okay, base is 1, right? Okay. And what is this? This side length right here is 1. Okay, that's also 1. And so if I focus on this little right triangle in here, would you agree that the height of the green triangle is the same as the height of that little slightly smaller right triangle?
Yes.
Okay, so if I could find the height of the right triangle, which might be easier to do, they would be equal. So if I just look at that little right triangle, let me draw it over here for a second. Here's what we know. That's x, and that's 1. What's the height of that thing? What's a trig function that might help me out? Sine might help, right? Because by SOHCAHTOA, sine of an angle is the ratio of opposite over hypotenuse. Okay, so sine x equals height, right? Let's just call that y, how about? Equals y over 1, right? So what's the height y equal to then? Sine x. Yeah, exactly. Sine x, isn't it? So if that height is equal to sine x, then the green area, thank you. Campbell. Who's Campbell? Right, Campbell? There you go. Okay. So then the green area, let's just call it A sub g for green, is just 1/2 times the base, which is 1, times the height, which is sine x, so just sine x over 2. Agreed? Okay. Okay, good. We got it. So there is the green area. Let's look at a big area. Let's look at this area of this triangle now. This blue one. This right triangle. Okay? So this is 1/2 the base times the height also, right? One base is still 1, but we got to find the height of this guy now. Okay, what's the height of that guy going to be? Now let's focus on that blue triangle for just a moment. So the blue triangle looks like this. Same concept. I want to know what y is. Is there a way I could define y in terms of a trig function? Tangent, sure, why not? Tangent by SOHCAHTOA, tangent equals opposite over adjacent. Okay, so then tangent x would equal y over 1, so the height is just tangent x?
Yeah.
Ah, okay, so now we got another area. So the blue area is equal to tangent x over 2. Okay,
Yeah.
agreed?
Yeah. See.
Now, in between, let's look at the area of this sector. This cardinal red sector. Cardinal red. Okay, so now that's the area of the sector. Is that us?
Yeah.
Oh, we're short today, aren't we? That's right. Oh, okay, we'll pick it up there. This is a really cool proof.
Cool.